Hello everyone and welcome to another video. Today I'd like to take a moment to talk about one of the most important concepts in controls engineering, and that's the idea of transfer functions. Now, if you spend any amount of time hanging out with control engineers, first off, congratulations on your discerning palate regarding your choice of friends, and secondly, you've probably heard this term of transfer function thrown around once or twice. When talking about transfer functions casually, this might mean a black box or an input-output model which relates how a specific input affects a specific other output of a system. So why don't we use a physical example to set the stage for this? So since I'm an aerospace engineer, I like to think about aircraft a lot here. So, you know, I've got an airplane here. This is a Piper Cub here, and there are many inputs to this system, right? Let's consider the system to be this aircraft flying along straight and level on a nice sunny day here at 10,000 feet above ground level. And there are many things that can be input to this system to influence the output. So for example, you notice it's got an engine here, so you can change the throttle setting to make this thing go faster or slower or climb or do other things. But there's also control surfaces like the ailerons here on the trailing edge of the wings. Those typically affect the roll of the aircraft here. You've got things like the elevator right here in the back here. That typically affects the pitch here. And then you've got other inputs like, say, like the rudder, which can also deflect. That rudder usually affects the yaw. Now, put a small little asterisk here when I'm doing this demonstration, because as you're probably already thinking in the back of your head, a lot of these inputs might affect more than just the axes that I was talking about here. But we're going to get to that in a second here. I just wanted to point that out and have it to be something you file in the back of your head for our discussion in a couple of minutes. So those are some of the traditional inputs to this system here, but there are other things that might influence how this thing flies. For example, what the air density is here, or the temperature here, or the weight of the aircraft. There's myriad number of different inputs that can affect the output of the system. Now, why don't we talk about outputs, right? As this thing is flying along, what are the outputs? Well, it could be anything you're interested in. There could be things like the velocity, or the angle of attack, or the angle of side slip, or the pitch rate, or the roll rate, or the yaw rate. There's a lot of different outputs that could come from this system here. So what you can think about here with this aircraft example is, why don't we think about just abstracting this here as a big model here. So I might have a big, let's just draw a picture of an airplane here. And again, I apologize, I am not the greatest artist here, so I'm probably going to butcher this here. So I don't know, let's just draw a wing here, fuselage, tail with the prop here, right? So this is my aircraft model. And like we said, there could be many inputs to this system here. So for example, let me make sure I got my numbering correct here so I don't go off base from my notes here. So, you could have something like, let's call the first input, maybe let's call it U1 here. This could be the deflection of the aileron. All right, there could be another input, U2 here. This could be your delta elevator that we talked about earlier. There could be another one, U3 here. This could be your delta rudder. U4 could be your deflection of your throttle, etc., etc., etc. And you could come all the way down to, like we said, there could be some esoteric inputs like, let's call it UN here. This could be like the air density, because that will affect the output of this system here, right? So in general, there might be like N inputs, right? And then what you've got coming out of this system here is multiple outputs. So I don't know, let's just start making some of these up here that might be relevant here. So I don't know, Y1. The first output might be something like your airspeed, right? Another output of this system could be something like your angle of attack. The third output here, let's call it Y3. This could be your angle of side slip. And again, etc., etc., etc. There could be many outputs. Like again, one of these could be, the weight of the aircraft might be an output of this system here. It could, right? You can conceivably write that as something you're interested in here. So again, you have N inputs and M outputs, right? So this model is undoubtedly very, very complex here, right? This aircraft model is probably this nonlinear ordinary differential equation with many, many states here. But if we're talking about just transfer functions, what a transfer function is talking about is picking one of these inputs and examining one of these outputs. So for example, you might be interested in, for sake of argument, what does the elevator do and how does that affect the angle of attack here? All right. So for example, what we typically talk about with a transfer function is a transfer function, or let's abbreviate this as TF here, right, is a input-output model describing how a given input affects a given output. So in this example here, right, where I want to look at the effect of, let's call it delta elevator, how that affects your angle of attack here, I'm really talking about how the second input affects the second output, right? So typically what you'll see this written is in this case, maybe I'll call this thing G22 for the second input affecting the second output here. And what you'll typically see here is this is basically a model which talks about how the angle of attack here, usually in the Laplace domain, is affected by the elevator here in the Laplace domain here. So we're going to see this in a second here, but I just want to conceptualize this and abstract this to, it's just identifying a single input to a single output here, right? Now, let's make a couple of notes here. Again, going back to this aircraft example here, let's talk a little bit about there, right? So this thing, this G22 here, this is probably a complicated relationship that's probably dependent on the states or the inputs of the system here, right? So let's say that this is likely a complicated relationship, right, that is dependent on the states or inputs to system. Right? So in other words, depending on how fast the aircraft is flying, what its current angle of attack is, what its current angle of side slip, what the current throttle, what the current rudder, what the current state of the system is going to affect how this transfer function behaves, right? Or how it's quantified here, right? The other thing to note here, maybe let's make this as point 1 here, and point 2 here is, as we talked about earlier, right? This single input that we're interested in, right, the elevator here, sure, it's definitely going to affect the output that we're interested in, namely the angle of attack, but it's very likely to affect other outputs besides the one that we're interested in. So let's just write that down first and we'll give an example here, right? So the input of Y2, right, which in this case was delta elevator, is likely to affect other outputs besides the one I'm interested in, right? Which, sorry, the input, this should be U2, right? U2 could affect other outputs besides Y2, which was the angle of attack here, right? So again, going back to our aircraft example, right? So this thing is flying along, and I want to understand how does the elevators, right, these control surfaces back here, how does that affect the angle of attack? Well, usually, you know, for those of you who are pilots, you'll probably know that, right? When you deflect the elevator, the pitch angle of the aircraft will change. Therefore, you'll change the angle of attack or the incidence between the air and the chord of the aircraft. But you'll probably also affect the airspeed, right? The aircraft might temporarily slow down as you pitch up here, and you may affect some of these other states simultaneously here, right? So that is something for another discussion here. For in terms of our transfer function, we are going to ignore all these other outputs and only zero in on the output we care about and how it is affected by the input that we're examining right now. All right. So that I think is a good discussion to set the stage here. Maybe what we'll do here is let's pause the video. I'll erase the boards and then let's take a look at mathematically defining a transfer function for a linear time invariant system, which is the majority of the classes of where we want to actually examine transfer functions. Okay, so let's take a more rigorous mathematical approach to defining and looking at transfer functions. So we said earlier that, when talking casually among control engineers, transfer functions are usually a phrase that means how does a given input affect a given output. Now, we need to get a little bit more specific here when we actually want to mathematically write down a transfer function. So in this particular scenario, we only want to consider linear time invariant systems here. And what I mean by that here is, let's just write this down for our definition here. So more precisely, a transfer function, right, of a linear time invariant system. What this is, it's defined as the Laplace transform of the input, or sorry, I guess of the output over the input, of the output over the input, assuming all initial conditions are 0. Okay? So again, all this is basically saying here is that this linear time invariant system means basically you have the system described by a linear ordinary differential equation of an arbitrary order here, right? And all we're going to do is look at that differential equation, take the Laplace transform, and basically just solve for this ratio of output divided by input here. So to give you an example here, right? So consider a general LTI, or linear time invariant system. And again, we saw that that's basically what you're talking about is a linear ordinary differential equation here, right? So a linear ordinary differential equation has this form here, right? So if we have y of t is the system output and u of t as the system input, right? What a linear differential equation looks like, it's basically derivatives of the output signal linearly combined. So on one side, so you basically have something like you might have the nth time derivative of the function here, right? And then maybe there's some linear constant in front. Maybe let's call this an, right? Plus, you might have the dn minus 1, dt n minus 1. So the n minus 1 time derivative of the function here. And again, you might have this constant an minus 1 in front. And you might follow this all the way down to you have something like a dy dt. And again, you've got an a1 constant here plus an a0 y of t, right? This is the linear differential equation portion here, talking about how the outputs and its derivatives must linearly combine. And that has to equal, again, some linear combination of derivatives of the input here. So again, you might have a, bm dm dt m of u of t, right? Plus a b0 dm minus 1 dt m minus 1 of u of t, right? Plus all the way down to b1 du dt plus b0 u of t. So again, this might look a little complicated because it's a very general format, but again, this is just what your typical linear ordinary differential equation would look like here, right? And now you know that in order to fully define this ordinary differential equation, right, since I have n derivatives here and m derivatives over here, I need to define n plus m initial conditions. So I need to define initial u's and their derivatives as well as initial y's and their derivatives. But we saw here that we're going to make this assumption that all the initial conditions are 0. We're going to see why we have to do that here in a second. So if you have this differential equation set up here, all the transfer function is you're basically going to take the Laplace transform of this entire thing and then solve for y of s over u of s here. So let's do that real quick here, just generally here. So what we said here is g of s, right? This is defined to be the Laplace transform of the output, all divided by the Laplace transform of the input, right? With the understanding that initial conditions are 0. Okay? So again, the Laplace transform of the output, we saw the output is just y of t here, right? So this is just going to be y of s, and the input here is just u of t, so its Laplace transform is u of s here. And again, this is with IC's is equal to 0, okay? So let's go ahead and take a closer look at this here. And before we do that here, and maybe this is going to touch upon this idea of why we need the initial conditions are 0 here, let's quickly refresh our memory here. If you remember one of our previous lectures, we talked about what is this Laplace transform operator, and we did a couple of Laplace transforms of common time domain signals here, right? The one that we're going to keep here, and the one that's going to matter here, that we talked about earlier was being incredibly important for control systems engineers here, was the Laplace transform here of basically the nth time derivative of a signal. So if you had some signal in time domain f of t, and you were taking its nth time derivative, right? Its Laplace transform here was s to the n of f sub s, right? Minus s to the n minus 1 here of f0 minus s to the n minus 2 ddt of f0 minus all the way down to dn minus 1 dt n minus 1 of f0 here, right? So let's box this up and remember this. This was basically the differentiation rule here of when you wanted to take the time derivative of any arbitrary signal here, right? Its nth time derivative here in the time domain. What that looks like in the S domain here or in the Laplace domain is basically derivatives in the time domain look like S's and their equivalent powers here in the Laplace domain. And then all of these, again, you be very careful. My handwriting is not the best here, and maybe I should be a little bit more careful here because this is a capital F sub s, and all these other ones are lowercase f's, right? So basically, to take the Laplace transform of this here, you need initial conditions in the time domain here, right? So these are the terms that we are all assuming to be 0 here in our transfer function here, because what that's going to allow us to do is all of these terms down here are not going to play a factor here. So I'm going to maybe lightly cross them out because we're going to make the assumption that that is 0, and this is 0, right? The initial condition of the signal is 0, and all of its derivatives here are all 0. So basically, you just end up with s to the n f sub s here, right? So anyway, let's keep this boxed up here, and we'll go ahead and do this here. So if you do that here, let's go ahead and maybe I will erase this bottom line. Here, and let's think about taking the Laplace transform of this entire thing here, right? So all we're doing here is you Laplace transform this entire left-hand side, and you Laplace transform the entire right-hand side here, right? And now we're going to make use of this property up here. So let's just maybe do it for one of these terms here, and I think you'll see the pattern here. So what I want to do here is let's distribute this Laplace operator through each one of these terms here, right? So let me do a few on this side, and I think you'll see what's going on. So Laplace transform of an dn y t and then dt n plus Laplace transform of basically this term here, right? Plus Laplace transform, well, I guess now we've got a bunch of dots, right? Plus Laplace transform of this term, plus Laplace transform of that term. Right, okay, I just want to focus on this one because, again, we do this thing once, you'll see the pattern, it extends to everything. So here, let's pull this thing out. We'll pull the constant an out. So I got an times the Laplace transform of dn dt y of t, right? Plus all the other garbage here that we're not even going to bother with here, right? Now, if you look at this term here, this is exactly what we have over here, right? It's the nth time derivative of the signal y of t, and I need to take its Laplace transform here. So, according to what we just said here, if I make the assumption that all these other initial conditions are 0, all this thing looks like is this term turns into an an s to the n y of s, right? Great. And then this second term here, if we had followed this down, it would basically have the exact same logic. You'd end up with an an minus 1 s to the n minus 1 y of s, right? Plus all the way down to, we'd end up with a1 s y of s plus A0 y of s, right? Is equal to, and then again, you would do the exact same thing on the other side here. So we would end up with a bm s to the m u of s plus a b0. Oh, I'm sorry. Wait a second. Sorry, guys. I screwed this up here. This constant should have been bm minus 1. Yeah, sorry, guys. Okay, this is bm minus 1 times s to the m minus 1 u of s plus all the way down to b1 s u of s plus b0 u of s. Great. And now you see this is the whole, again, we talked about this with the Laplace transform lecture here, but the beauty of the Laplace transform is it took an nth order differential equation and reduced it into a bunch of algebra here, because you can see I can now solve the left-hand side for y sub s, right? So if I do that, I end up with, what do we end up with here? We end up with an s to the n plus an minus 1 s to the n minus 1 plus a1s plus a0, and I can pull out the y of s, right, is equal to, again, same thing on the right-hand side, solve this, basically just factor out use of s, and we end up with bm s to the m minus 1 plus bm minus 1 s to the m minus 1 plus all the way down to b1s plus b0, and I pull out use of s. And at this point, it's basically solved for the ratio now of y over u. And maybe I'll do this in this big blank space here. So we end up with y of s over u of s is just going to look like bm s to the m minus 1 plus bm minus 1 s to the m minus 1 plus yada, 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 all the way down to b1s plus b0 all over an s to the n plus an minus 1 s to the n minus 1 plus a1s plus a0. Gosh, there we go. And we said this earlier, this is the transfer function here of the system. Okay, so pretty much every transfer function for a LTI system that we're going to be dealing with is going to take this form here, right? It's going to be some polynomial in S as a numerator over a polynomial in S in the denominator. And again, the thing that you're typically going to see here is n is greater than or equal to m. So the order of the denominator polynomial is typically going to be strictly greater or equal to the order of the numerator here, right? Great. So let's see here. Maybe let's write down a couple of properties of transfer functions before we go into maybe a concrete example here, because I know this is, with all these indices, this might be a little bit complicated here, but I wanted to keep it general to start with, okay? So let's come over here. Let's erase this and we'll write down a couple of observations and properties of transfer functions here before jumping in. Okay, so the first thing about a transfer function that is actually very helpful to remember here is that it's almost restating the fact that we wrote earlier here. So let's just write down properties of transfer functions. So one here, right? It's basically a math model, right? It's a mathematical model. Model. This is horrible handwriting. Model that relates output to input, right? I mean, that's exactly what this is doing. It says, here's the output, here's the input here, and that's our mathematical model, right? It's this ratio of polynomials here, right? Two here, the transfer function is a property of the system, not the input. So over here, you notice we never actually picked and said that the input is a ramp, or the input is a sine wave, or the input is a step, right? This is how the system responds by itself here, right? So what's nice about this is you can think about this as a characterization of the innate properties of the system. So going back to our aircraft, right, we would have a transfer function for the aircraft. You don't have a transfer function for the aircraft with a specific type of input, right? So this is nice because this captures the response or the characteristics of the system subject to any kind of input, which we'll see here in a second, okay? Three here. Let's see, what is the other thing then? The transfer function includes necessary units, right? But it doesn't provide any insight into the physical structure of the system, since it's only an input-output model here. So let's say it includes necessary units, but does not provide insight into physical, let's say maybe / internal structure, since it is only an input-output model. So again, going back to that aircraft example where we said we were interested in how does the elevator affect the angle of attack here, right? What that model is going to tell us, it's going to tell us, yeah, here's, if you do something to the elevator, here's what the angle of attack is going to do. But it doesn't tell you the mechanism by which that occurs. It doesn't, you don't understand if, does that mean the aircraft pitches up first? What does the throttle do? What is the internal state of the system during this maneuver, or anything like that? It just tells you, if you give me a specific input, it will give you a specific output. And again, that example here talking about the units here, right? We said delta elevator, which probably has units of like, I don't know, degrees, right? Or something like that. How does that affect the angle of attack, which, well, I guess in that example is also degrees here. So I guess that transfer function would be unitless here. But in some case, you might be relating how does the gas pedal position of your car, which is measured in, I don't know, fraction of a percentage between 0 and 100%, how does that affect the speed measured in miles per hour, right? That's some funky unit conversion, but the transfer function will have all of that unit conversion built in here. Okay? Let's see, and probably the most important thing here about a transfer function here is if the transfer function is known, right, then the output for a given input can be predicted, right? Then output to a given input can be predicted, right? That's probably the most important one here, because we're going to use this a lot. That's the whole point. That's why people love transfer functions, because it's basically a very simple model that we can use to predict output to any given inputs here, right? Oh, maybe let's do one more here. 5 here. What's interesting here is if you don't know the transfer function, you can experimentally determine it here, and we'll talk about that in a little bit greater detail in a different lecture here. So if TF is unknown, you can experimentally determine it, which is nice here, okay? Okay, so that's some properties of the transfer function. Let's go ahead and maybe do an example here, a concrete example of a very well-known system that I think everyone in dynamics and controls is very familiar with here, and I think will give us a better handle on how does this system behave here. Okay, so the system I want to look at here is, let's use our good old friend, the mass spring damper. Right, and I've assumed that you guys have seen this so much that I really don't need to go into great detail about this, but let's say you've got some mass here hooked up to a wall through a spring, K here with as well a viscous damper with viscous damping coefficient C, and let's say that you can apply a force on this thing, U of T here, right? So you can apply some, maybe there's an engine or a thruster or something like that, or you can just grab this thing and kind of apply a force in the horizontal direction here, okay? Let's say I'm interested in measuring the output, which is the position of the block here, okay? So this is the position, and this is the output. And here, U of T, this is like our forcing function here, or it's the input to the system, okay? So the first thing we're going to do here is get equations of motion for this thing, and given the number of times you've seen this, I'm not going to derive it here, but I think you'll believe me when I say that the equations of motion for this thing are something like my double dot, here's your mass times acceleration, is basically equal all the forces. Let's put all of the viscous forces here, and the spring force over here, and maybe we'll move the external force on the other side here. Okay, so here you go. My double dot plus cy dot plus ky is equal to U of T, right? This is your very standard differential equation here, which describes this block. Okay, so now let's go ahead and take the Laplace transform of both sides here, right? That's typically what you would do here, right? If you watched our other lecture on Laplace transforms and partial fraction expansion, basically, and solving ordinary differential equations, right? We see that this is a second order linear ODE. I'm going to use the Laplace technique to solve this exactly here, right? So let's go ahead and Laplace transform both sides. Okay, so I need to go ahead and take the Laplace transform of my double dot of t plus cy dot of t plus ky of t is equal to the Laplace transform of u of t, right? I don't know what the input is yet, so we're going to keep it general, okay? So again, let's do that same trick we did earlier. Let's distribute the Laplace through to each one of these terms. So I could write this thing as m times the Laplace transform of y double dot of t plus c times the Laplace transform of y dot of t plus k times the Laplace transform of y of t is equal to, let's leave the right-hand side. I'm not too concerned about that yet. And now here, well, crap. Unfortunately, I just erased the differentiation theorem, but I think we can remember it from memory here, right? So the second derivative of a signal here, right? Let me put some parentheses here. This is going to be s times y sub s, right? Minus, oh, sorry, this is s squared, right? Because there's two dots here, there's two derivatives. Minus s times y0 minus y dot 0. Okay? Okay, that's this term. This is exact. We have made no approximations yet, okay? Now, here and then you get c times this term, which is going to be s times y sub s minus y0, right? Great, and then I got this last term, which is k times y sub s is equal to the right-hand side, which is just u sub s. Great. So we are, again, we haven't made any approximations yet. This is the normal Laplace technique. So usually what you would do with the Laplace technique, right, is you would plug in your initial conditions. You would then plug in what your input was. Like you would take the Laplace transform of the input, solve for y of s, and then perform partial fraction expansion and inverse Laplace transform and all that kind of good stuff here. But make a note here, if we're trying to do this from a transfer function perspective, make it, try, I dare you right now, try to solve for the ratio of y of s over u of s. And you're not going to be able to do it because these initial conditions are hanging around. And this is what's going to be the, I don't want to call it a debilitating disadvantage of a transfer function, but it's definitely one of the disadvantages is we need to make the assumption that these initial conditions are zero. So we have to assume here that, again, this term right here, notice the notation, right? This is a capital Y of s. This is a lowercase y of 0. This is the initial position of the block in the time domain. So did it start here in the middle or did it start 2 meters off to the right? That's what this number represents. We have to assume it starts there in dead center, right? Similarly, this right here, lowercase y dot of 0, this is the initial velocity of the block. Did it actually have some velocity going in the left or to the right, right? We can't represent that with a transfer function. We have to go ahead and assume that this is 0. Similarly, I have to assume, here we go, this thing is 0. So we had to make that assumption of all initial conditions are 0. And we better write that down here because that's a key part here. So we have to assume ICs are 0. And maybe let's underline this so you don't forget it here, because again, this is one thing where we're losing fidelity at this point here, right? We're making an approximation. Now, if we do make this assumption though, notice here, what does our equation come out to be? It comes out to be this nice form that actually you can solve for that ratio of y of s over u of s. Right? So we end up with this thing looks like what? It's ms squared y of s plus csy of s plus ky of s is equal to u of s, right? Great, now I can factor out the y, so I end up with ms squared plus cs plus k is equal to u of s. And now just solve for y over u, and we end up with, well, we end up with 1 over ms squared plus cs plus k here, right? This here is our transfer function, which relates and is a mathematical model that will tell us how does this force here on the brick or on the block here affect the position here. And again, it is not particular to any given input yet, right? We haven't done nothing yet. We haven't said that the input is a step or a ramp or a sine wave or anything like that. And in fact, maybe that's what we should do right now. We should see, how can I use this information to predict the behavior of the system? So why don't we jump over to Mathematica and actually do that, because I think that'll be a little bit quicker than me doing it on the board, and it might actually be kind of interesting. Let's go ahead and assume some constants here for these values here. So let's assume the block weighs a mass of, I don't know, 1 kilogram here. The damping coefficient is 3 here, and the spring constant is 5 here, right? Let's just pick some numbers so we can numerically approximate this here. And what we want to do here is, let's go over now and think about, again, from a graphical perspective here. Now I've got this G of S here, right, which is my mass spring damper system. Right? In goes some kind of arbitrary forcing function, and out comes the position of the block here, right? So what I want to do now in Mathematica here is investigate, how can we use this mathematical transfer function model that we developed here to predict what is the output to different kind of inputs. So maybe let's try two things here in Mathematica here. Let's say that this is like a step input, and then maybe also a sinusoid. And let's see, how do those different inputs affect the output here, using this transfer function to describe this. So I'll pause the video and I'll meet you over there on Mathematica.
All right, so the first thing we probably want to do here is go ahead and define the transfer function. Okay, and I believe what we said earlier, if you remember, is that the TF is given by, let's just write it down here in text so we know what we're trying to do. I think it was 1 over ms squared plus cs plus k. Right, that was our transfer function. This is kind of hard to see. Maybe let's zoom this in a little bit so we can maybe see a little bit better. Okay, there we go. That was our transfer function. So let's go ahead and define this in code now. So G of S is 1 over ms squared plus cs plus k here. And maybe what we should do first is let's go ahead and define some of these constants here. Right, which was, I think M was 1, let's suppress the output, C was 3, K was 5 here, right? And then we can go ahead and define the transfer function. So let's shift enter that to get that into Mathematica. Great, so now what we can do is, once we have the transfer function, we see that we can go ahead and evaluate the response due to a, let's do something simple to start with. How about a unit step here, right? And let me see if I can spell evaluate correctly. Okay, there we go. So if you recall here, what we want here, a unit step is given by, right, u of t, it's just 1, right? So in the time domain, it's just a signal that looks like just unity at time 0 here, right? So if we wanted to, we could take the Laplace transform of this to get what this signal looks like in the Laplace domain, right? So I would go ahead and take the Laplace transform of 1, right? And if you remember here, that is just 1 over s here. So in this case, what we want to do here is just go ahead and define this input. So how about u of s is just going to be 1 over s, right? There we go. And now what's so great about the transfer function here is that the transfer function, whoops, if I could spell this right, will allow us to predict the response to this input, right? So in other words, y of s, we said, was just going to be the transfer function times the input here. So in other words, this is going to basically be this, right? Here's g of s times, here's what we said u of s was, right? And that gives us the response in the Laplace domain. So let's go ahead and do that right now. So y of s is just going to be g of s times u of s. So here we are. This is the response of the system in the Laplace domain. Again, this is kind of helpful, but it doesn't, it's not very intuitive. So at this point, we could do some of those techniques we talked about earlier, right? You could identify the roots of this complex polynomial and figure out what the appropriate partial fraction expansion is in order to do the inverse Laplace transform. But let's just use Mathematica to do this for us to get this in the time domain here. So let's just go ahead and say, use Mathematica to get this from the S domain to the time domain, right? So in other words, I want to say inverse Laplace transform of y of s, go from the s to the time domain. That is going to give me the signal in the time domain here. So let's just do that. And here we are. We see that this block, the way it's going to respond here is you can see that there's a constant, and then there is it looks like a decaying sinusoid, right? Right here, here's the sinusoid portion, and then you've got this decaying exponential here. So maybe let's go ahead and plot this so we can see what this looks like here. Let's go ahead and say plot y of t from time t 0 to 10 seconds, just so we can see what this looks like. Oh, and Mathematica looks like it cut this off, so let's go ahead and change the plot range. Whoops. Plot range to all. Ah, come on. ALL is how you spell all. There we go. And here you go. So this is what the system looks like in response to a unit step. And again, this looks completely reasonable, right? If you remember, the transfer function said that this is a model of the system at 0 initial conditions. So yeah, if you look down here, the block starts at 0 and the slope down here is 0, but subjected to a unit step. And what it's going to do is it's going to move and eventually come to steady state at some location away from the block, which again makes perfectly good sense if we think about the physical system here, which was this mass spring damper here. Okay, so now what we can do is let's also continue exercising and show why this is so useful to have the transfer function. Namely, what we can do here is let's go ahead and evaluate. Again, I have a hard time spelling evaluate for some reason. The response due to a sinusoid. Sinusoid. There we go. So in other words, let's go ahead and choose a different input here. Whoops, sorry. I'm trying to turn this cell to text here. So we're going to choose an input of, let's make u of t, I don't know, let's make something up. 5 times sine of 2t. How about something like that, right? Okay, so again, if we follow our technique above, what I need to first do is I need to get the Laplace representation of u of t. Right, so in other words, I need to take the Laplace transform of this. So again, let's use Mathematica to help us with that. So Laplace transform of 5 times sine of 2t, going from the time to the s domain here. This gives me u of s. Right? So here we go. This is what it looks like in the Laplace domain. So now we follow the same thing we did earlier. To get the output is simply y of s is the transfer function g of s times the input that I'm interested in, which in this case is 10 over 4 plus s squared here. So again, we can just do this. Y of s is g of s times u of s. So here is what it looks like in the Laplace domain. Let's go ahead and use Mathematica to get the inverse Laplace transform of this to get it in the time domain. So I can say inverse Laplace transform y of s from the s to the time domain. Again, this gives me y of t. And here we go. That's a little bit more complicated. I wonder if I can simplify this a little bit. Simplify. Well, I guess it is what it is here. We see that there's a decaying sinusoid out here of this frequency, and then at steady state, like we expect, we end up with a sine wave here, which has the same input frequency as, or sorry, the same output frequency as the input frequency, as the frequency of the input here. So again, let's go ahead and plot this here to get a better idea here. Plot y of t from time t 0 to 10. And here we go. So I hope this shows you how this is very helpful to have the transfer function, how we can evaluate all of these here and use the transfer function to predict the behavior of this block here or this system under any given under any given input here, with the caveat that the initial conditions are all 0. Okay, so now that we saw how to do this in Mathematica, maybe just to round out the experience, let's look at how we can analyze this exact same system here and look at using transfer functions in Matlab. So let me pause the video and we'll switch over to Matlab. All right, so here we are with Matlab. So let's just go ahead and explore how to use transfer functions in Matlab and Simulink. Okay, so let's start off with our clear CLC close all. And now let's go ahead and define the constants of the transfer function. So just like we did in Mathematica here, let's just say the mass is 1, the damping coefficient is 3, and the spring constant is 5, okay? So now what I want to do here is I want to create a transfer function object in Matlab. So we can do this using the tf command. So what I mean by that here is MATLAB uses a vector of coefficients of the numerator and denominator to represent a transfer function. So if you remember here, the g of s that we're trying to create here is 1 all over m times s squared plus c times s plus k, right? That was our transfer function here. So if you notice here, the numerator is really simple. The polynomial, it's just a 1 here. So let me just go ahead and make a variable called, how about gnum? So to represent that numerator of just 1, I'm going to use a vector of just 1. So that's actually ridiculously simple. Now the denominator now, you notice here, in terms of the coefficients of s in descending order here, you have a m, a c, and a k. So in other words, to represent this denominator here of ms squared plus cs plus k, the way MATLAB is going to represent that here is with an m, c, and a k. All right? So what this does here is this 1 by 3 vector represents this second order polynomial. Okay, so what I mean by that now is you can go ahead and call the TF function, and if you pass it the numerator polynomial and the denominator polynomial, this will return an object called g, which is a transfer function object. So if I go ahead and just run this right now, let's go ahead and run this. Okay, and we see here, look at this. G is actually this special object here, and if we come here to the workspace, you can see that it's a 1-by-1 transfer function object. In fact, if I bring up the class here, you'll notice here that this is a TF object here, right? So this is great here. What the TF object is going to allow us to do is do some of that analysis that we talked about earlier. So for example, we can subject the system to a unit step input. So remember earlier in Mathematica, we saw that we had to go ahead and Laplace transform that unit step, and then we had to multiply the transfer function by that unit step in the Laplace domain. Then we had to inverse Laplace transform it to get it in the time domain. And then we had to plot it. Well, in Matlab, we can do all of this in one simple step here. So I'm going to start a new figure here, and then I'm just going to say step. I'm going to go ahead and call the step command, pass it the object g, which is a transfer function, and what this does is when I run this, it will bring up a plot, which is basically the step response of the system. And if you see, this is exactly what we got earlier. I guess in Mathematica, we ran it for 10 seconds. This only went for 3.5 seconds here. So there are ways that you can change this. I'll let you go ahead and read the documentation on steps so you can read about how you can change the period, for example. So if you look at this, says t final, we can go all the way up to, let's go ahead and make a t final of 10 seconds. So this should be, it's very similar to what we did in Mathematica now. So if I run this again, here we are. This looks beautiful, right? This is exactly what Mathematica got us. Okay, now let's go ahead and how about do the sinusoidal input, right? Let's go ahead and subject the system to a sinusoidal input. I think in earlier we used u of t was, gosh, I'm going to probably mess this up. I need to check my notes. What did we use here? It was something like, 5 times sine of 2t, I think. Was it 5 times sine of 2t? That was what we had. Now, unfortunately, there's not a real good, clean, easy way to do this here within MATLAB. However, we can easily do this within Simulink. So let's go ahead and start up Simulink. Here we are. Here's Simulink. I'll start myself a blank model here. And let's go ahead and what we can start doing here is I'll pull up the Simulink library browser. Sorry, these keep opening in separate windows on my machine. Maybe I'll put this off to the side. Okay, now what I can do here is in Simulink, I can go ahead and actually, if you come here to continuous, you'll notice here that there is a transfer function block here. So if I grab, drag, and drop this into Simulink, and let me zoom in a little bit so we can get a better picture here, we can get this transfer function object here. So if I double click on this, you see that it's basically the same thing. I just need to give it a list of numerator coefficients. And in fact, since this is already defined in the MATLAB workspace, I'm just going to say gnum, and the denominator coefficients is just going to be gden. If I hit apply, okay, and I get this transfer function here, which should basically be the g of S that we defined earlier, right? So now what I can do is, whoops, sorry, whoa, Nelly, hold on, let me delete some of these. Let's go ahead and grab some sources here. Like, for example, let's get this unit step here. We'll maybe first recreate the unit step in Simulink before moving on to the sinusoid here. So let's grab a scope to hook up on the far end. And come on, here we go. Okay, great. And now let's make the step time to be 0, the final value of 1. This all looks great here. Let's make the final time 10 seconds. Yeah, that sounds great. And if I hit play, and now look at the scope output, here we go. This looks like the Simulink response, and here is the step response that we got from Matlab. So again, these things are virtually identical. The flexibility of Simulink here, and why I like Simulink a little bit more, is because it's much more flexible and robust. So for example, if I didn't want just this step input, I can now here go and find, here we go, how about a sine wave? Right? And let's make this thing the sine wave we wanted, which was amplitude 5, frequency of 2 radians per second. Hit apply, okay. I can even come in here and maybe let's grab a manual switch here and allow the user to pick which input do they want to go into the block here. So right now, this is still the normal step input, but with a quick flip of the switch here, we can change this here to have a sinusoidal input, which again, if we compare this now with our Mathematica notebook, it should be virtually identical to what we did earlier. So great. I think this is a pretty good spot to stop here. Why don't we go and take a quick look at a summary slide of what we discussed here regarding transfer functions, both the conceptual as well as their usage in Mathematica and Matlab. Okay, so to summarize what we discussed today, we started off by talking about transfer functions of general systems, and we saw that when you're talking about transfer functions with controls engineers, they might be talking about more complicated nonlinear systems, and really what we're discussing here is the relationship between a given input and a given output of a system here. Now, the type of transfer functions that we're more interested in, because we have some mathematical tools to deal with, are transfer functions of linear time invariant systems, or basically transfer functions of systems that can be described using a system of linear ordinary differential equations. And we looked at how to actually compute the transfer function of a general LTI system. We then looked at an example using a mass spring damper system, which is a pretty classic LTI linear ODE system here, and we saw how you can get a transfer function between a given input and a given output of that system. Then we looked at some of the implementation of how to work with transfer functions. We first looked at using them in Mathematica, and we saw that really this is just using Laplace manipulations here, because a transfer function is really just a Laplace transform of the output over the Laplace transform of the input. Then we moved on to how to work with transfer functions in Matlab, and we saw that there were some built-in tools where you don't even have to leave the Matlab environment here to build a transfer function object and to do things like subject it to a step input. However, if you wanted to get more complicated or more flexible here, it definitely makes a lot of sense to figure out how to work with transfer functions in Simulink, as this is probably one of the best environments to explore transfer functions and their input-output relations. So, that was what we covered in this video, and I think this sets the stage very nicely for some of our upcoming discussions. Particularly, the next lecture will be talking about block diagrams of how we can compose multiple transfer functions together into a complicated block diagram, and even do some manipulations to compress and simplify that complicated block diagram into something a little bit more understandable. So I hope you'll join me at that video. If you liked the video, please go ahead and hit the like button and subscribe, and I really hope I will catch you at the next lecture. Until then, I'll talk to you later. Bye.